Welcome to Wireless Fundamentals, Session 6, Basic Configuration. So far in your training, we have covered many aspects of how wireless works in theory. We are finally going to work with actual WLAN products and learn about basic configuration. Finally, some reality to go with our theory. Administrators can use three methods to configure an HP Unified Wired WLAN controller. You can access a graphical user interface, or GUI, via a web browser, or manage the AC via the IMC WSM platform. However, for initial access, the command line interface is a good option. You can use the CLI interface directly by connecting your laptop to the AC's console port. This is typically pulled off by connecting a USB to serial adapter to your laptop. You then connect the DB9 female connector of a serial cable to this adapter and plug in the RJ45 connector of this serial cable into the console port of the AC. Your USB serial port should be configured for 9600 baud, 8 data bits, 1 stop bit, no parity, and no flow control. You then install and run a terminal emulator software package on your laptop, such as HyperTerminal, TerraTerm, PuTTY, or Secure CRT. You can access this same CLI via a network by using Telnet or SSH. Note that SSH is disabled by default. However, some engineers prefer a direct console connection for initial access to a new controller. This allows you to have everything set up and connected before you power on the device. It is a good idea to watch a device boot from start to finish, especially when you are first learning. By getting used to seeing a normal boot process, you will be more prepared to identify something that is not normal. Once your console connection and terminal emulation software are ready, you can connect a power cord to the AC and plug it into a power outlet. The unit powers up. Listen to it power up and note that the power LED is lit. The device initializes itself and begins to boot. When prompted, enter a country code. This should typically be for the country where the AC is installed, but we will discuss this further in a later lesson. You will see a message that says, press enter to get started. Press enter here, and then again when you see the prompt HP. You are now ready to begin configuring and managing the switch via the CLI interface. The figure shows a typical unified AC deployment. The HP 830 8-port model is represented. One of the two functional components inside the unified controller is a switch engine. On the 830 8-port model, physical interfaces GE1/0/1 through 8 are PoE-capable ports that can be used for connections to end systems and APs. Interfaces GE1/0/9 and 10 are available to be used as uplink ports to your wired Ethernet infrastructure. The other functional component inside this unit is the access controller engine. The wired switch engine and wireless controller engine are unified inside the unit with internal Ethernet ports. The switch engine ports GE11 and 12 connect to AC ports GE1 and 2. These internal connections can form a link aggregated connection. The two components communicate over this internal link using Open Application Platform, or OAP, technology. The need for OAP depends on device model. This is not required for the 10500, 7500, 20G WLAN controllers, but is currently required for the HP 830 series. With the 830, each engine runs a separate COMware-based OS with separate SNMP agents and management interfaces. The console port connects to the AC engine. You can then use the command OAP connect slot 0 to access the switch's engine CLI. Use Control K to return to the AC. You can remotely access each engine's CLI via Telnet or SSH, although SSH is not enabled by default, and via GUI, HTTP or HTTPS interface. The default IP address of the AC and switch engines are 192.168.0.100 and 101 respectively. The default username and password is admin. The figure shows a typical example of that portion of the initial configuration used for connectivity between the switch and AC engines. The configuration of management interfaces is also shown at the top of each configuration. Beneath that, each device is configured with Interface Bridge Aggregation 1, set to trunking with appropriate VLANs permitted. Of course, these VLANs would need to be configured along with interface configurations. This configuration is not shown, as some level of experience with the ComWare CLI is assumed, and the focus here is on initial AC to switch connectivity. Next, you can see that the internal interfaces are configured as members of the Bridge Aggregation 1 group. Once you have configured the basic settings on the HP 830, you can associate APs to the controller. APs can be connected to various switches throughout the organization. In the graphic, AP3 is connected directly to an 830 switch port, which is configured to support native or untagged VLAN 1. AP2 is connected to another switch port, which is also configured to support untagged VLAN 1. This places the APs and the AC in the same VLAN or broadcast domain. This means that the APs can use a simple broadcast mechanism to discover the AC. As an AP boots, it typically uses DHCP to acquire its IP addressing info. Then it sends out a broadcast. Since the AC is in the same broadcast domain, it receives this broadcast and responds to the AP. While this method is very simple to deploy, it is not very scalable. It is okay to have 10 or 20 APs on the same subnet as your controller. However, you would not want 800 APs on the same subnet. Larger deployments can leverage a Layer 3 discovery mechanism. You might have 50 to 100 APs on a special VLAN reserved just for APs, say VLAN 21. Another 100 APs might be on VLAN 22, and another 100 on VLAN 23, and so on. This makes for a very scalable, robust design. However, when AP1 broadcasts a discovery request, the AC will not receive it, since they are in different broadcast domains. We need some other mechanism to enable APs to discover their controllers. You can customize the configuration of your DHCP server to fill this need. The DHCP server will send the AC's unicast address to the AP. You could also modify your DNS server to fulfill this need. Or you could statically provision the APs with the IP address of its controller. We will discuss these options in more detail soon. For now, it is enough to understand that the HP Unified Wired Wireless Controller is very flexible and allows you to create a very simple solution for small environments and a scalable solution for large environments. Using either an Layer 2 broadcast or Layer 3 assignment mechanism, APs will find the appropriate controller and provide WLAN services. Also understand that an AP request to join the controller will be rejected unless an AP template has been defined. The controller doesn't trust any APs that you, the network administrator, did not tell it about. For unified ACs, The APs cannot join and become managed until you configure AP templates. One option is to enter each AP's model number and serial number individually. This can be tedious if many APs must be deployed. The figure shows enabling the Auto AP feature and configuring an Auto AP template for a particular AP model number. Using this method, you only need to configure one template for each AP model to be controlled, as opposed to a separate template for each individual AP. Here's how you configure Auto AP using the CLI. First, the feature is enabled, and then a template is defined with an arbitrary but hopefully descriptive name, such as 2620E AP. The model number is selected from an available list, and you can use the question mark to see this list. In this case, the WA2620E was selected. The next command is serial ID auto. This informs the AC that it should accept all APs of this model number regardless of serial ID. If you prefer to individually specify each AP, you would enter the AP's serial ID number here instead of the keyword auto. Finally, the country code is entered. This can also be accomplished via the AC's GUI. First, the feature is enabled by navigating to AP, Auto AP, then navigate to AP Setup to first configure and save the template. Then modify the template by adding the country code. It is a best practice to remove the Auto AP template configuration once all APs are discovered. This ensures that you remain in control of which APs join the AC. The figure shows how to determine which APs have joined the AC. You can use the CLI command display WLAN AP all, or navigate the GUI to AP Setup. Note that you see the Auto AP template and the single AP that is joined in this scenario. The APs are automatically named after the AP template with an _000X appended, where X equals the join order. It can be very useful to create AP groups. This allows you to configure a collection of APs to support the same SSIDs and VLANs. For example, you may want APs in the lobby to only support the guest SSID mapped to VLAN 19. The APs in the accounting building should not support the guest SSID, only the corp SSID mapped to VLAN 11. The APs in the engineering building should also support the corp SSID. However, those users should be mapped to VLAN 12 on the wired network. You can define AP groups directly from the AC GUI. Navigate to AP Group. From here, you can add a new group or modify an existing group. In the figure, a new group named Site A is configured. Certain APs from the AP list can be selected and moved to the selected AP list. This makes those APs a member of the group. Next, you can choose which SSIDs are to be supported by this group of APs. The figure also shows the same configuration created from the CLI. Once you have APs properly joined to the controller and organized into groups, you can begin to configure SSIDs. Recall that SSIDs used for a guest solution should probably be configured for central access control for security reasons. SSIDs to be used for corporate access should use a distributed or local forwarding model for scalability. Let's start by looking at a central forwarding solution. First, you define a WLAN ESS interface. Remember, wireless users end up on a wired VLAN at some point. You have to configure which VLAN should be assigned or mapped to a particular SSID. Virtual Interface WLAN ESS1 is created as an access port on VLAN 19. Next, a WLAN service template is defined as a clear SSID, which means wireless user traffic is to be transmitted in the clear without encryption or other security features. The SSID is defined as guest. So far, you have defined the wired side, interface ESS1, on VLAN 19. You have defined the wireless side, SSID guest, which is an open, unencrypted WLAN service. Now you tie the two together. The virtual interface is bound to the service template. Thus, wireless clients that connect to the guest SSID are mapped to wired VLAN 19. The AP does not perform this mapping by default. Unless otherwise configured, all traffic is tunneled to the AC. For an actual guest solution, this is probably what you want. The interface binding command is being shown here, so you know you could do it if you wanted to. To function, the service template must be enabled. Next, you enter the radio configuration context for an AP or AP group. This is where you bind the service template to the radio of an AP or group of APs. In this case, it is bound to radio 1 of a single AP named APA. This is the 5 GHz radio, which of course must be enabled. If you also wanted this SSID to be supported on the 2.4 GHz radio, you would apply the service template to radio 2. To configure local forwarding, Virtual Interface WLAN ESS2 is created as a hybrid port. PVID 21 is configured. This means that wireless clients are assigned to this VLAN, but this could be overridden when binding the service template to APs. VLANs 3 and 21 are listed as the VLANs that are allowed to be used should this override option be selected. Next, a WLAN service template is defined as a clear SSID, and the SSID is defined as corp. The AP is also made responsible for performing authentication locally. However, since this SSID is a clear type, no authentication is performed. The beacon SSID hide command ensures that this SSID will not be included in periodic AP beacons. The virtual interface is bound to the service template. The command client forwarding mode local VLAN 21 informs the AP that it is responsible for locally bridging traffic from the SSID to this VLAN. As before, the service template must be bound to AP radios. Since the AP will be forwarding WLAN traffic onto the wire with 802.1q tag equals 21, the attached switch port must of course be configured to support this VLAN. The AP itself must also be configured to support this VLAN. This is accomplished by creating a text file to serve as a managed AP configuration or map configuration. This is then applied to the access point. In the figure, a file named localforward21.cfg was created and then uploaded to the AC's flash memory. The contents of this file is shown. The service template is bound to an AP with the command service template 2. If you wanted some APs to map this SSID's clients to VLAN 3, you could override the default VLAN assigned with the port hybrid PVID VLAN 21 command. You do this on an AP or group of APs with the command service template 2 VLAN ID 3. With central forwarding, the client traffic is tunneled to the AC, which unwraps the native client frame and forwards it onto the wired network. Therefore, the wireless client's MAC address is learned from the AC. With local forwarding, the AP locally forwards client traffic directly onto the appropriate VLAN. Therefore, the client's MAC address is learned from the AP. To summarize, once the infrastructure is in place and APs are assigned to groups, it is a four-step process to defining wireless network support for corporate employee or guest access. 1. Define the VLAN parameters in a WLAN ESS interface. 2. Define the WLAN parameters in a service template. 3. Map WLAN to VLAN when you bind the WLAN ESS interface to the service template. 4. Assign the service template to an AP or group of APs. The figure provides a high-level review for key unified AC configurations. You can navigate the left-hand column of the unified AC GUI by clicking on Device. From there, you can perform the following. Basic. Configure the name of the AC and set things like the idle timeouts. System time. Configure time, time zone, and time protocols. SNMP. Configure communities, traps, and/or SNMP v3 parameters. Interface. View and configure physical and logical interfaces. You can also navigate the left-hand column of the unified AC GUI by clicking on Network. From there, you can perform the following. VLAN. Define VLANs. Configure physical ports. Assign VLANs to ports. IPv4 routing. View the route table and define static routes. DNS. Define static and dynamic DNS options as well as DDNS. Service. Enable and disable FTP, SFTP, Telnet, SSH, HTTP, and HTTPS. Finally, diagnostic tools allow you to perform IPv4 pings, IPv6 pings, and traceroute. The previous page provided an overview of several useful areas to discover and assess an existing unified AC deployment. Of particular interest is SNMP configuration, since this is a prerequisite to adding the AC as a managed device in the IMC platform. The figure shows a typical configuration geared toward SNMP v2 deployments. Community strings are defined and system information is configured, as is a target host for trap messages. With the 6 sessions covered so far, you should have a good, well-rounded understanding of both WLAN theory and concepts, as well as practical deployment and configuration. This then prepares us to learn about more advanced topics such as radio resource management, client roaming, and WLAN security. All of these more advanced topics rely on tight integration and cooperation between access controllers and access points. In the next session, you'll learn how APs find and connect to ACs, and understand how to ensure that ACs properly accept, configure, and manage APs.